Hello, everybody. So this will be my first video, hopefully, of a longer series where I'll be discussing the IB analysis and approaches high level and technically also standard level course. And I'll be going over the topics, hopefully all of them over time. But yeah, I'm going to start going over all of them as a booster course. My name is Vinhal. I am a tutor and I've been a tutor for IB for about 6 years. And all of my students, they've gone from like grade twos, threes to sixes and sevens. And so I felt like, maybe I should just have a more open source kind of approach. So here we go. The topic we're discussing today is differentiation. So I'm going to basically take you through everything you need to know about differentiation. And just by watching this one video, you will know everything you need to know to be able to solve past exams. So now, what is the whole like premise of differentiation? It starts with the simple humble gradient. Okay. So at this point, if you're talking about differentiation, you should already know what a gradient is. A gradient is basically, if you have a straight line, you can find the slope of this straight line by just checking the rise over run, right? So the slope is the rise over the run, and it's basically the rate of change of y in terms of x. What does that mean? It means as x is going, like as you go one step to in the x direction, how far up or down do you go, basically? That's what the slope or the gradient is. They mean the same thing. So technically speaking, we can consider this the rate of change, and that is essentially what we are trying to get when we differentiate a function. Okay. Now here's where the trouble arises. Of course, if you have a straight line, you can just pick any 2 points on the straight line, like x1, y1, and x2, y2. And you can just find the slope as the difference in the y values and divide it by the difference in the x values. And that'll be your slope or your gradient, same thing. Okay. However, the problem arises in advanced mathematics where you don't have straight line functions anymore. For example, to explain why we need differentiation, let's take a random function, f of x equals x squared, the humble parabola. Simple guy. It looks like this. Now, the problem here is that, for instance, if I want to find the slope of the function, I am no longer talking about one single value like I was in the straight line case, because the straight line has the same slope everywhere. The way you can like kind of intuitively visualize it is, imagine a person standing on this graph. They would have multiple, like if no matter where they stand on this graph, you will notice that they will feel the same steepness, right? However, if they stand on different points on this parabola, they will feel different steepnesses almost everywhere, right? In fact, no 2 points will have the same slope on this parabola, because if you stand here, you're feeling a slope downwards of this much, and if you're standing here, you're feeling a slope upwards of this much. So the slope changes constantly. So now the discussion is no longer about finding a specific slope at a specific point. The discussion is about finding, sorry, the discussion is not about finding the slope of the entire function, because it's not a constant number, but it's about finding the slope at a specific point. For instance, this point. Okay. In order to find the slope at a specific point, what we do is we go through a thought experiment that is very common, a very common method to calculate or derive things in algebra. So, for example, let's say the point you want to find the slope at is x, which would mean that the y value at this x value is f of x. Okay. In fact, for this specific thought experiment, we don't even need to define the function. We can just think about a random function f of x, arbitrary. Now, since the only way we know how to find a slope is by using 2 points, let's stay with that kind of assumption and choose another point some distance away from the initial point. Let's say that distance is h, which would mean that this point is x plus h, because you're h away from x, so you're at x plus h, which would mean again that your y value is f of x plus h. Okay. Now, of course, if we were to just, assume for a second that the line between these 2 points is a straight line, we can find the slope using the same idea as before. The slope would be the change in the y values divided by the change in the x values, right? So y2 minus y1 over x2 minus x1. And that would simplify to this over h, because the x's would just cancel out. However, of course, the thing is they are not the line connecting these 2 points is not a straight line. That was the whole point, right? Because it's a curve. So this is a curved line. So by finding this slope, we're essentially finding the slope of a straight line between these 2 points, but that's not what we have actually. So what do? We say that if h, meaning if the distance between these 2 points is in like small enough, then we can approximate the line connecting those 2 points as a straight line. Because think about it. If these points are super close together, mathematically speaking, if they're infinitely close together, meaning the distance between them is not quite zero, but almost zero, right? In that case, the line connecting these 2 points would essentially be a straight line, which would mean mathematically, I can say that limit as h approaches zero. This is the definition of a derivative. What does that mean? What did I just do there? Basically, I'm saying that you take that expression that we developed earlier and take h to zero. Don't make h zero, make it approach zero, meaning make it go so close to zero that it's indistinguishable from zero itself. So essentially, this is the formal definition of a derivative. Okay, I will make a separate video where I will go over thorough examples for all of these things. But for now, let's just do one quick example. We'll use the same example that we used earlier, f of x equals x squared. Now, if we directly apply the formula, this is what the formula would look like. F of x plus h, which would be what happens if we plug in x plus h in place of x into the function, it would give us this. And then minus f of x over h. This is what you end up with. Now our goal is to solve this solve this limit problem. So the first thing when you're solving limit problems, hopefully I'll make a separate video about how to solve limits, but for now, assuming that you guys are, familiar with the basics of them, you have to open this up. So expand this, x squared plus 2xh plus h squared minus x squared over h. Simplify as much as you can. So the x squares canceled out, and that leaves you with 2xh plus h squared over h. And now you can take the h line, factor it out from the top, which would leave you with this. And the reason we did this is because all along I could not directly plug in h equals 0 because there was a division by 0 happening. So now I can cancel these out, and that leaves me with a much simpler looking limit, one that I can actually plug in h equals 0 to, and it would just give me 2x. Now the smarter among you will realize that the derivative of f of x is indeed 2x, using the power rule that you might be familiar with, but we will learn about that in a bit. So this is how you can use the formal definition of a limit to find out formal definition of a derivative. I believe this is actually called the limit definition of a derivative, but honestly, these are unimportant things to me personally because I am more focused on figuring out how to use them. But anyways, yeah, limit definition of a derivative, this is how you use it, and that's what it is. So I hope that this makes sense to you. So now the question arises. So we had a function earlier, f of x equals x squared, and we found this new function, which I wrote down as f with a little apostrophe, right? We call this apostrophe a prime, f prime of x. And we got that the derivative of my function is 2x. Okay. But the question is, what is a derivative? What does this function mean, right? So let's talk about what this original function meant in the first place. What does a function what does a function do? It takes an x value as an input and spits out the corresponding y value on the graph of that function as the output. Okay, that's what a function does. What does a derivative do? Similarly, it takes an x value as an input, but instead of telling you the y value at that input value, it tells you about the slope at x. So for instance, your graph looks like this. F of x squared looks like this. So if I plug in, for instance, 1 for x, f of x, meaning the main function itself, it'll tell me that the y value is 1. Because it is. 1 squared would be 1. It would give me an output of 1. However, the derivative function would tell me that when I plug in x equals 1 into the derivative, it's going to tell me what the slope of the graph is at x equals 1, which is 2. So there's a slope of 2 at this point, right? So that's a tangent and a tangent to the graph will tell you the slope of the graph. So if you draw a straight line that is touching the graph only at x equals 1, that straight line will have a slope of 2, because the derivative is what tells you about the slope of the graph at any given x value. That's what a derivative does. So this is called a derivative, and every derivative belongs to a parent function. So this is its parent function, basically. Okay. Now, I'm going to teach you about differentiability and checking for differentiability by using this example. A function is differentiable at any given x value if the derivative from the left side and from the right side is the same using the limit definition of the derivative. What does that mean? Very long sentence. It basically means that if I use the definition of a derivative and I use it from the left side, or if I use it from the right side, I should get the same, I should get the same answer from both ends. Okay. And this is always worth checking at any point that the function is changing behaviors. So notably, you can notice that in a piecewise function, it's very important to check at the point where they are exchanging behaviors. So from when x is positive, it's x plus 2. When x is negative, it's x squared plus 3x. So at x equals 0, it is useful to check whether your function will be differentiable. Now, let's talk about both of these one by one. Basically, if I'm talking about h being negative, right? So h is approaching 0 from the left side, which means that, for instance, I mean, not for instance, actually, we're checking at x equals 0, right? So at x equals 0, if I take the original point at x equals 0, so basically at this line, then the other point, since I'm approaching h from the negative side, the other point would be somewhere here, okay? Which means that I'm looking at the left side behavior of the function, which means that this will use the second version of the function because that is the part where x is negative. So when I'm approaching from the left side, I need to use the left side part of the function, which would mean that my limit turns into this. F of x plus h would be x plus h squared plus 3 times x plus h over h, and equals, on the right side, since I'm approaching h from the right side, I will use the right side function, which would mean that I'm using x plus 2 as my function, which is going to be x plus h plus 2 minus x plus 2. Be careful here. Make sure you put them in brackets. I made a small mistake here. I forgot to subtract the actual function here. So it's going to be x minus x squared plus 3x, because this is f of x plus h, and that is f of x itself. And that leaves us with this. And over here we have divided by h also. The goal is to find out what both of these end up being and checking if they're equal. So let's open all of this up. X squared plus 2xh plus h squared plus 3x plus 3h minus x squared minus 3x. All of this is divided by h. Let's do any cancellations that are possible. There. And since I see that this guy has an h in him, this guy has an h in him, and this guy has an h in him, I can cancel this with this, and this, and this, which leaves me with 2x plus h plus 3. Okay. On the left side, that's my limit. And on the right side, it's looks easier. X plus h plus 2 minus x minus 2 all over h. The negative x and the x cancel out. The negative 2 and the 2 cancel out. The h and the h cancel out. Does not give you 0. Be careful. It gives you 1 because h over h is not 0 but 1. So on the right side, I end up with a much simpler limit to solve, which is just this. On the left side, I end up with 2x plus 0 plus 3, which is just 2x plus 3. And on the right side, I end up with 2, which means the derivative from the left side is this function, and the derivative from the right side is this function, and they're clearly not equal, right? Especially when I consider that I'm checking the differentiability at x equals 0. If I plug in x equals 0 on both sides, because I'm checking the differentiability at x equals 0, I will get 3 is equal to 1, and it's not equal, which means that not differentiable at x equals 0. And again, just to clarify, why am I checking at x equals 0 specifically? Because at x equals 0 is where trouble seems to be happening. The function is changing behaviors. Okay. If you look at the rest of the graph other than x equals 0, this is just a simple smooth function. So it has derivatives. It's clearly got defined slopes. And if you look at this part of the function, it's a straight line. It's a constant slope. In fact, that is why we got 1, a constant number on the right side, because the right side of the function has a constant slope. It's a straight line. And that is it. That's how you check differentiability of a function. Just check the left-hand side, h approaching 0 from the left-hand side, h approaching 0 from the right-hand side, and make sure that you're plugging in the right functions depending on which side you're coming from. Now, the next few parts of this chapter are basically 80% of what shows up in an exam. It's about how to use the simplified rules of differentiation to find the derivatives of functions easily. Because of course, nobody has time to go through all of this just to find a simple derivative. So we have simplified rules formed that we can, generalize to all cases. So rules for differentiation. There's a lot of rules, and most of my students get this overwhelming feeling where they're like, how am I supposed to remember all of these things? The thing is, you have to get some hands-on practice because it becomes muscle memory at some point. You know how you just know that 2x plus 3x is 5x? Same way, at some point, you will just start to understand these once you have done enough questions. So the first rule is called the infamous power rule, which is, if this shows up in an exam, you would be very happy because this is the simplest kind. If you have an algebraic term, this is important, an algebraic term, not an exponential term. Just to remind you, an algebraic term is where the variable is sitting as the base and there's a numerical power at the top. This is an algebraic term. An exponential term is when there's a number at the base and there's a variable in the power. This is exponential. This is algebraic. Okay. Now, the power rule applies to algebraic terms. If you ever see an algebraic term with a coefficient and a power, simply to derive this guy, multiply everything by the power of x, and then subtract 1 from the power, and that is literally it. There's nothing more to it. For instance, minus 2x to the power of 3 over 4. To derive this, all you have to do is multiply everything by 3 over 4 and subtract 1 from the power of x. So 3 over 4 minus 1. To simplify, you can simplify this, cancel the 2 and the 4 and whatever. 3 over 4 minus 1 would be negative 1 over 4 if I'm correct, but my mental math is maybe not the best. This is it. That's the power rule. The next rule that we need to discuss is the chain rule. The chain rule is mostly used along with many other rules at the same time. A lot of people teach it a lot of different ways, but honestly, I mean, not to brag, but my method, I feel like, has gotten all of my students, like they understand this immediately. The chain rule is best taught using an example, but first let me tell you the general version of it. Whenever you see a function that is trapped inside another function, now that other function that is it's trapped inside could be a power, it could be a sine or a cosine, etc. It could be anything. But for now, let's just stick with powers because that's all we've talked about so far. So if, for example, in this scenario, if you want to derive this, what you do is just ignore the inside for a second and imagine that the inside was just x. What would happen? It would just be n because you multiply by the power, whatever's on the inside, and subtract 1 from the power. So that's the first step. Ignore the inside and just apply the power rule, and then multiply this whole thing by the derivative of the inside. If you remember it this way, it can be applied to many different scenarios immediately. It's very, very easy to understand. For example, let's say you have 2x squared plus 4x, and it's all raised to the power of 1 over 2. Now, the first thing you do is derive the outside, meaning just imagine that the inside is just x and derive this part, which would mean that you have 1 over 2 times whatever is on the inside, ignore that for a second, and subtract 1 from the power. And then multiply by just the derivative of the inside, which would be 4x plus 4. That is it. That's the chain rule. The next rule we need to discuss is the product rule. The product rule applies when you see two separate functions being multiplied with each other. For instance, f of x is getting multiplied by g of x. In this case, normally you're going to see it as two separate factors basically that are separated, and you can consider each of them a separate function. To derive this situation, you can actually just do this. Derive f of x and multiply by the original g of x, plus derive g of x and then multiply by the original f of x. And that's it. So the way I write it normally is just u and v. If you can figure out, what is u and what is v, the derivative would just be u prime v plus v prime u. Very easy to see in an example. For example, 2x squared plus 4x times x plus 5. To derive this, first understand what is u. U is 2x squared plus 4x, and then understand what is v. V is x plus 5. So u prime would be 4x plus 4, and v prime would be 1, because the derivative of v is this, the derivative of u is this. Now just apply it. So u prime v plus v prime u. That's it. Easy peasy. This is how you use the power rule, the product rule, sorry. The last one that you need to know about is the quotient rule. The quotient rule is basically, similar to the product rule in the sense that instead of multiplying two functions, you see two functions being divided. By the way, as you can see, it's very easy to see when two functions are being multiplied. They'll be clear factors, but if it's not, then you'll see some examples where you might, have to kind of dig a bit deeper, but it's mostly going to be pretty obvious. For the quotient rule, you're going to see a similar situation, but the functions are being divided from each other. Now, as you can see, it doesn't really matter which one you write first in the product rule, u prime v or v prime u. Either of them can come first because it's just an addition. But in the quotient rule, the order matters. You're going to have u prime v and then minus v prime u. If you do it the other way around, you're going to get, it's basically wrong. And then divided by v squared, and that's it. So for example, if you have x plus 2 over 2x squared plus 4x, and you want to derive this whole thing, first figure out what u is. U is always the top, v is always the bottom in the quotient rule. So u prime would just be 1, and v prime would just be 4x plus 4. Now just put it all together. So u prime times v minus v prime times u, and divide this all by v squared, which is 2x squared plus 4x whole squared. And that's it. That's how you use the quotient rule. So as you can see so far, by the way, that's all the rules that you need to know for differentiation. Now, the thing is, we've only discussed algebraic functions and algebraic things, meaning x to the power of something, etc. But there are other kinds of functions that you will be dealing with in differentiation, maybe even more often than algebraic ones, in AA at least. The first one is the exponential function. The exponential function, again, is a very big misconception is that the exponential function is specifically the guy with the e at the base. That's not true. An exponential function is any function that has a number at the base and a variable in the power. That's a very general thing to say. How do you derive an exponential function? Let's set up a very arbitrary one, meaning any random number at the bottom, a, and any function at the top. Whenever I say function, just think about any mess created with x in it. Okay, so this is a function, this is a function, this is a function. All of these are functions. So any basically just operations done on x, that's a function. So for example, if this is the thing you want to derive, then you have to follow something very similar to the chain rule actually. First off, whenever you're trying to derive an exponential, write down the same thing again. Exponentials derive to themselves to begin with, and then multiply by the derivative of the power. So as you can see, this feels like the chain rule because you're doing the outside first and then multiplying by the derivative of the inside. And just one last step, also multiply by natural log of whatever the base is. Okay, so if a is the base, natural log of the base. Okay, so this is the derivative of an exponential function. For example, e to the power of 2x squared plus 4x, if you derive this, would simply be the same thing written again, multiplied by the derivative of the power, which would be 4x plus 4, and then multiplied by natural log of the base. Now, remember that natural log of e is just 1, so don't forget to Simplify it because otherwise it looks more complicated than it actually is. That is your answer. That's how you derive exponentials. Now, then you have trigonometric functions. Thankfully, they work the same way. So you do the outside first and then the inside. But before we talk about these, you need to know the basic derivatives of sine, cosine, and tangent. Remember that sine will always derive to cosine, cosine will always derive to negative sine, and tangent will always derive to secant square. With that said, let me show you an example of the situation. In general, by the way, first, if you have sine, for example, of a function. So there's a function trapped inside a sine. Again, this is me foreshadowing that we're going to use the chain rule. To derive this, just derive the outside first. What do I mean by the outside? Meaning sine. What's the derivative of sine? Cosine. So the inside stays the same for now. Nothing happens to the inside according to the chain rule. And then once you're done deriving the outside, multiply that by the derivative of the inside and you're done. That's it. So for example, if you have sine of, or let's say tangent, just to give you guys something more substantial to work with, because it's going to look more complicated at least. Tangent of this, if you derive this, first do the outside. Tangent becomes secant square. Inside stays the same for now. And then multiply this by the derivative of the inside, which would be 4x plus 4. And that's it. That's how you derive any trigonometric functions. And the next function that we need to discuss is the logarithmic function, specifically the natural log. So deriving the natural log. So if you want to derive the natural log, it's simple. Again, in general, you have a natural log of a function. So as you can see, the function is trapped inside the natural log. So to derive this, first derive the outside. Now, remember, whenever you derive the natural log, you end up with 1 over the inside. So this is the derivative of the inside, okay? Sorry, the outside. So when you derive the natural log, you end up with 1 over f of x. But then you have to multiply by the derivative of the inside, which would just be f prime of x. So for example, if you have natural log of 2x squared plus 4x, you would end up with 1 over 2x squared plus 4x, that's the outside done, times the derivative of the inside, which would just be 4x plus 4. And that's it. That's how you derive natural logs. And finally, the derivatives of inverse trigonometric functions. This is where people get really scared. Trigonometric functions. So first, I'll tell you, just like before, I'll tell you the basic derivatives of the basic functions without any functions inside of them. So you have arc sine, which is also famously called sorry. You have the arc sine. We're talking about inverses. And then we have the arc cosine. And then we have the arc tangent. So these are the inverse functions. And the derivative of arc sine is simply 1 over root of 1 minus x squared. The derivative of arc cosine is simply going to be minus 1 over root of 1 minus x squared. So thankfully, that's easy to remember. And then finally, the derivative of arc tangent will be, just a second, 1 over 1 plus x squared. This is how you can get all the derivatives of inverse functions. Now, what if you don't have just x inside them? What if you have a whole function inside them? You can use the chain rule. So for example, if you have arc sine of f of x, it would simply be 1 over 1 minus, instead of x, you have f of x, right? So f of x squared. But remember to multiply by the derivative of the inside, like that. So as you can see, once you master the chain rule, these are all common sense. So again, since the arc cosine is just 1 over minus 1 over root of 1 minus x squared, but now you have f of x in place of x, so you write down the exact same thing, but with f of x in place of x squared. But remember to multiply by the derivative of the inside. So just one extra step really. And the arc tangent of f of x would simply be 1 over 1 plus the square of the inside, but remember to multiply by the derivative of the inside. Remember, these are derivatives that I'm trying to calculate, so kind of misleading writing it equal, but yeah. These are the derivatives of inverse trigonometric functions.